Welcome back. We're going to continue now working our way through the consolidation, just like that, consolidation worksheet, which is special relativity 4B part 2. In a previous video, we did questions 1 through 3, so we'll now focus in on 4 and hopefully 5 or 6. Okay, so let's look at question 4 and see what we can do with it. Rightio, a spacecraft, which is given as a proper length of 80, is travelling past a space station at the speed of 0.7 c. Its radio receiver is on the tip of its nose. That's interesting. And the space station sends out a radio signal the instant the tail of the spacecraft passes the station. I think I need a diagram to unpack that. So let's look at the first question and see if I need what I need to do. What is the length of the spacecraft in the reference frame of the station? So in other words, it's just what is the observed length of the spacecraft as observed by the space station. So let's do that one there. That seems to be quite a straightforward one. Okay, so let's do question 4. So 4a. Now the first thing we need to do here is that our velocity is 0.7 c. So let's work out the gamma for 0.7 c. It will be given by this expression there. Let's type that in. So it is 1 over the square root of 1 minus 0.7 squared, and that's nearly exactly 1.4. Okay, we'll just make it 1.4. Rightio. Now, we need to work out the length. Now, we know that the length of velocity is equal to the proper length divided by gamma. So here we have our spacecraft. Let's put it there. And here is our space station. And you are observing that space station there. Okay. And apparently there is a radio receiver on the nose. Okay, so I'll put that there as well. If you're on the spacecraft, you observe the proper length of this craft as being 80 meters. Okay. But because you are stationary, well, you consider yourself stationary on the space station, you see this length here as being contracted. So let's work out that length. So the contracted length would be its proper length, which is 80 over 1.4. And let's do that now. So it's 80 divided by what we just got there. So it's 57.13 meters. Okay, so we would observe 57.13 meters. Okay, now let's have a look at question B, which, okay, so let's put it up here. What is the time taken for the radio signal to reach the nose of the spacecraft according to those on the space station? Okay, let's do that. So there was a statement about when the space station sends the radio signal. It's the instant the tail of the spacecraft passes the space station. Okay, so I'll draw that. So I've got it really there again. So we're going to make these two things align. So there's the space station, and here is the spacecraft. Okay, right. Immediately, this space station sends out a radio signal. Okay, at the point of this alignment. At a certain time later, which we'll call just time equaling t, the signal has moved all the way through to this point here. At the same time, the spacecraft has also moved to this point. When these 2 points are at the same level, the signal from the space station will be received by the radio receiver here. Okay, so when that spacecraft has moved to here, it will receive this signal after time t. Okay, so it's after a certain period of time, they will be, this signal here and this position of the spacecraft will be identical, and that means that they'll receive the radio signal. Okay, so let's work out what this distance would be. So we want this distance here, to equal this distance here. Okay, so we go back to fundamentals. Velocity is distance over time, so distance is velocity times time. Now let's go down to this one over here. So the velocity of this radio wave, remember radio waves are electromagnetic waves and therefore go at the speed of light. So the distance here would be the speed of light times this time that we're talking about that it will take here, so CT. Okay. Now, what would be this distance up here? Obviously, it's the same as this distance, but in reference to the spacecraft, it would be equal to this length here plus this distance here. Now, this distance is 0.7 because it is not the speed of light, so it's 0.7 c, that's the speed, times the time taken for the entire actual passage of time, which we're saying is t. Remember, it's already here. It's already got a little head start, and this head start is 57.13 meters. Okay, so let's make those equal each other. So the bottom distance, let's move that up. The bottom distance is CT, and the top distance, remember these two distances are the same, would be 57.13 plus this section here. Now, the craft is traveling at 0.7 c, so that's its velocity, times the time taken for the entire action to happen, which is still t. Okay, so these two things must be the same. So 57.13 would equal, oops, let's not equal, let's undo that, plus 0.7 CT equals CT. Okay. Now change sides. We've got 57.13 would equal, that's going to give us, that's one lot of CT, and this is 0.7, so that becomes 0.3 CT, giving us time equaling 57.13 over 0.3 C. Okay, let's see what that does. So it's that number there, which is still on my screen. So it's that number divided by 0.3 times 3 exponent 8. So, okay. That's 634.8 nanoseconds. Let's have a look at what the answer says. Oh, it's in microseconds, so I'm going to undo that. So that equals 0.634 microseconds. Okay. Right, yeah. So it will after 63 microseconds, the signal has moved to here. After 63 microseconds, this point here has moved to that point there. Right. So let's have the next question. How far from the space station is the nose of the spacecraft when it receives the radio signal from the frame of reference of the space station? Well, all it's asking is, what is this distance here? Okay, so that distance, d, would equal CT. It doesn't matter. We'll just use CT because we know the speed of light is always constant and we know the time. So it's 3 by 10 to the 8th multiplied by 0.34 microseconds. There's my calculator. So that's times 3 exponent 8. So that's 190.4 meters. So this actual distance is 190 meters approximately, a little bit more